Hello, everyone. Thanks for coming for this session on a Friday. Hope you've enjoyed the conference so far. My name is Denzil. I am first of all, the formalities, silence your cell phones, please. And then the next one is, I hope you've already explored what PASS has to offer. And PASS is more about the community than the conference. So there are virtual chapters and things of that nature. So feel free to explore that. My name is Denzil. I am a program manager in the Azure SQL team, and I focus primarily on Hyperscale. And so today we'll talk about Hyperscale in quite a bit of depth. We'll look at the architecture of Hyperscale, why this was built, how it was built, the different components. This is not your regular SQL Server, how we architected this to scale out, build resiliency, and handle fault tolerance and things of that nature. Right? So the second thing we'll talk about is some of the scenarios that it enables besides the OLTP scenario. We won't cover OLTP because we know that Azure DB does fine there. And then we'll look at some diagnostics and migration tips, if you will. So we'll look at what's different in troubleshooting some of Hyperscale-related performance things. We won't cover. We're assuming everyone has worked with SQL, at least in this room. and so how many of you are actually using Azure SQL today? OK, so about everyone. So we'll not focus. We'll touch on maybe one or two things from an Azure SQL perspective, which are also relevant. But we'll predominantly look at Azure SQL database. Huh? Anyone is using Hyperscale today? Wow. OK, 1, 2. I'd love to chat with you after this talk and get your experiences and learn a little bit more about your workloads as well. So we'll talk about diagnostics with regards to what's specific to Hyperscale. What have we enabled you to see from this distributed architecture as you troubleshoot performance problems? Right? So some of the large challenges with database exist. Right? Provisioning storage to expand the database is a problem. Today you can go to the cloud, but we are limited with 4 or 8 terabytes in our other non-hyperscale offerings today. It's 8 terabytes on managed instance, it's 4 terabytes on business critical. Today. We are coming up with larger SKUs, but still the problem is still you'll have to shard, and sharding adds some complexity to the applications, if you will. Then other operations like restore can take a while. If you restore a database, it's the size of data operation in most places. On-prem, you may have SAN snapshots and things of that nature for the VLDB databases that facilitate things, but it can be a problem otherwise. And then degradation, ability to scale out and scale up in a constant time is a problem. Provisioning hardware on-prem is a problem. In business critical today, even when you scale, you might reach on another node, and so it's a size of data operation. So you have to seed that new replica before you actually switch. And then scaling compute, we talked about that. Moving to a larger box is a problem. And economics of scaling and sizing for your peak workloads can be a problem today, right? So what's Hyperscale? So Hyperscale is architected for the cloud. So it's not a single instance SQL Server as we know and love SQL Server today. So it's split apart into components and architected for the cloud with resiliency. Right? So storage, we have multiple levels. We have tiered storage pretty much with multiple levels of caching. It starts with the slowest storage, which is Azure Blob storage, and then you have 2 more layers of caching to enable the I/O that you need and IOPS that you need and the speed that you need for these VLDBs. Then there's compatibility. So your surface area really doesn't change. It's just Azure SQL Db. Right? So whatever works on Azure SQL Db works on this. And pretty much it's 98% of what surface area for on-prem also minus agent. This is the single database offering that we're talking about here. Scaling up, storage and compute scale separately. So you can have a 2 core compute sitting on a 20 terabyte database. if you're not using. So there's a separation of what, storage is not tied to the tier of your compute. These are two separate layers of separation, if you will. And then there's large database support. We support today up to 100 terabytes. This is a limit that we'll work on raising as there's demand. Internally, there's no logical reason why we have to stop at 100 terabytes today. The architecture allows us to scale further than that, but this is what's currently supported. And then we scale out with replicas. So today we support up to 4 readable replicas, where you can scale your read workload horizontally. And there are scenarios to do that as well. And then there's performance benefits of Hyperscale. So a couple of things to do with Hyperscale. Some of operations are offloaded to this layer called page servers, and we'll look at it in the architecture. Things like checkpoints and backups are no longer done on your compute. So that frees up some resources on the compute to service your workload. Then restore is in constant time. So irrespective of the size of the database, restore is done with snapshots, and so that's in constant time as well. And then there's accelerated database recovery, which enables some of this quick scale up, scale down type scenarios. So if you have a long-running transaction, your scale up or move to another node is not long like it could be without it. Yeah, go ahead.
If we need to take this question offline, I understand.
Absolutely.
But I read the white paper.
Uh-huh.
I understand the use case comparatively to existing transactional workloads, but I can't get a straight answer on why not Hyperscale instead of the SQL DB part of what is now Synapse, because it seems to me this gives you everything that you would want in DW and then some by virtue of the fact you get the full surface area of T-SQL.
Sure. So the question was effectively why not Hyperscale instead of DW or Synapse? If we can hold that, we have a data loading section. There are some limits around kind of ingest, right, which you can't get around. This is full recovery model. It's single ingest point. There are certain limitations which for certain workloads may make this a better target. Now, if it's a smaller warehouse, a smaller mart, I don't have a problem with Hyperscale, right? So, and it's SMP versus MPP too, right? So DW is MPP. So if you have a large query, which is a single query is still limited to a single compute on Hyperscale, right? So whereas on MPP system, a single query can be distributed across multiple computes. And that doesn't make a difference if it's a smaller warehouse, right? I mean, but it can make a difference if it's a petabyte scale or hundreds of terabytes type queries. Oops, I think I went ahead of, okay. So let's look at a few features that make this possible. We have this thing called a resilient buffer pool extension, or RBPX. Back in, I think it was 2012, we introduced buffer pool extensions, which allowed you to, at that time, memory was not as prevalent as it is today. It allowed you to actually extend your buffer pool onto SSDs, right? But this is more than that, because this is resilient across failovers. So in this, we store metadata actually in hackathon tables or in-memory OLTP tables to know what pages are in that buffer pool. So across failures, this is resilient. Then you have snapshot-based backups. Again, this was introduced in 2012. You can have a file on Blob, a database file on Blob. You can have a VM with a file on Blob and take a snapshot backup of it. And actually, for those running VMs, actually, that's a great solution from a backup perspective. So that's how we do backup. And accelerated database recovery, I'm not going to go into. There's a session for that, and you've heard it in the keynote. So other than that, this is a high-level view, and then we'll drill into each component. So you have an external log service. So the log service, actually, and the log itself is not local anymore, right? So this log service process is not a SQL Server process, actually. It's a new process. And we'll dig into that in a bit. Then you have a set of one or more page servers that constitute your database. So if your database is 10 terabytes, there are as many 10 terabytes divided by 128 gigs of page servers. So each page server hosts 128 gigs of data. This is a fully covering cache of your data, right? And it's tiered. It's the first level cache. I guess the first level is the cache on compute. The second level is the tiered storage, which is covering. And then you have completely separated, Azure Blob storage, which actually holds the data for long-term retention, right? So if all the components above fail, your data is still in Azure, Blob storage, and it can be read. And each component at each level has, actually, we won't talk about compute for a second, but each component does resiliency at the storage level, there's resiliency at the page server level, so each page server will have another instance of a page server, if you will. Right? And then similarly, the log service also has a corresponding blob for long-term retention, which simulates more of the infinite log. You won't run out of log space because there's not a size associated with it. And then last but not the least, it's the page server's job, right there, to then, all the writes actually go to the log service. There's no writing from compute to page servers. The log service, in turn, then ships those log records to the page servers and to the replicas. And you can have, 4 replicas, that make up the ecosystem. Storage is encrypted at rest. So if you don't need a compliance reason for TD, and if you need TD, by all means, use TD. But we have had customers that don't need TD for a compliance reason because storage is still encrypted at rest. You can save a little bit of the overhead of TD. I'm not saying don't use TD. I'm saying storage is encrypted at rest here. So let's drill. Yeah, go ahead, question.
Can you use your own TD encryption key?
BYOK is, I have a roadmap slide. It's coming. OK, can you use your own encryption key? Not yet is the answer. We have it on the roadmap. Hopefully, we can close that gap. Yep.
Is it possible to go to the previous slide?
Yes.
The question is, when do you acknowledge that the update took place?
Hold on. I have detailed slides on each component. This is just like overview. Was there another question? Are we good? OK, let's move on. So the primary. The primary has, of course, you have a buffer pool, which is in memory. You also have this component called RBPX cache, which is a non-covering cache on primary. So besides your memory, your most recently used data is also on compute, so we don't even have to leave compute to actually go to page service to fetch it. And that cache is non-covering because we have only this much SSD, which is shared by TempDB and RBPX on the compute node itself, right? So we use LRU algorithms to see how often you've used it and so on and so forth. So this is a non-covering cache. It doesn't cover all your database. It's just your most recently used data, right? So the primary can scale up from 2 to 80 cores, configurable. As for Azure SingleDB, we've just previewed the M128. It's just a matter of time that some of the slows that or tiers that come in Azure SQL DB will also come in Hyperscale, right? So memory and directly attached. OK, so the memory and SSD is proportional to the cores. What I mean is the RBPX cache and the memory is proportion of the cores. And the vCore limit is this article on vCore limits actually states for each tier how many gigs of mem you get and how much of RBPX you get. Memory is also dependent on hardware generation. We support 2 hardware generations, Gen 4 and Gen 5, so the ratio of memory to core is a little different, so check those out as well as you make your decisions. Then for RBPX, the local, since it's SSD, your latency is 0 to 2 milliseconds. I put 1 to 2 milliseconds to be conservative, but it's 0 to 2 milliseconds unless you're hitting IOPS limit, which gets you to be throttled, which we'll talk about in a second, right? For read-write workloads, all read-write workloads actually go to the primary, and readable workloads can be scaled out across the secondary. OK, so the second thing is readable secondaries. Readable secondaries are currently the same size as primary, so there's no current option, at least, to size the secondary as a separate tier than the primary. Okay, so it has I'm not going to cover it still has the same characteristics of the primary in terms of RBPX cache, in terms of memory, in terms of cores. You can scale up to 4 readable secondary replicas. And then read-only workloads can be routed to it by specifying application intent equal to read-only in your connection string. The distribution across the replicas is a round-robin distribution. So request 1, request 2, so on and so forth is distributed across the replicas. And they are a hot failover target. So if there is an unfortunate incident where something goes down, whether planned or not, right, they become a failover target, right? This doesn't mean if you don't have a replica, you don't have availability, but it adds to the SLA. So for example, if you have 0 replicas, today your SLA is, I believe, 99.99. With 1 replica is 99.95. With 2 replicas, it's 99.99. And the reason is, in a case where it's not a planned failover, for 0 replicas, we still have to spin up the compute, right? So we spin up compute, and then we attach to those page servers. So if compute goes down, it's not like page servers go down. The page servers are still there. We just spin up new compute and have leases on the page servers, and off we go with life. But if we already have a replica which has those leases to the page server, it's a little bit quicker transition from that perspective. The other thing is replicas are priced at Azure hybrid pricing, so they're cheaper than the primary, unless you have A-Hub for the whole thing. But replicas are priced differently if you're paying full price for the primary. Then let's go to page servers. Do a quick time check. So page servers are a SQL Server.exe, right? So it's like compute. It has SQL Server binaries on it. It's a remote SSD, if you will, in the sense that the page servers are computes, are nodes, right, with the local SSD. And they cover the whole database in their local SSD. So it's not Azure Premium Storage with remote SSD. It's the local SSD on those page servers itself that have those chunks of data. And the chunks are 128 gigs in size. Right? So this is covering, as I said, so you have 10 terabytes, you have this many page servers, you have 20 terabytes, you have even more page servers. So it's divided by 128 right now. So this can be anywhere from 1 to 10 millisecond latency. It kind of depends on the load and how much you're reading from each page server, right? So ideally, when you're not reading from only one page server, because if you're reading a set of pages, they could be distributed across. If you have to do a remote read, right? If it's not there in local cache and you got to do a remote read, you would be reading from one or more page servers. So latency is a little bit more than RBPX. Each page server corresponds to a single database file. So if you look at sys.database files, you have a file for each page server, which is 128 gigs. And each of those page servers correspond to a file or blob on Azure storage. So there's a corresponding blob on Azure storage for that page server. And then, like we said, checkpoints are offloaded to page servers. Backups are offloaded to page servers. They're not done on compute. So for checkpoints, we use indirect checkpoints, which is the default now for SQL Server, even on-prem, which steadily keeps track of the dirty pages and flushes it to Blob in this case. And so there's no direct, all the writes to Azure Blob are not done from compute. All the writes are done from page servers, right? So. And then there's built-in high availability, and hence the multiple page servers. So each page server does have a replica. So something happens to the page server, the replica takes over, right? So and then so that's the thing about page servers. The other aspect, okay, I think I have it on another slide, so I'll wait. Allocations are in 10 gigs increment. So you don't specify max size or anything of that sort. If you grow, we grow in 10 gig chunks, if you will, as you're reaching, your limit of what is currently allocated. We'll just add another 10 gig chunk as you need it. Okay, now on to the log service. The log service effectively doesn't have a size. It provides an infinite log abstraction. it consists of 3 components, really. One is the xlog process, or the log process, if you will. And this is not SQL Server. The second one is a landing zone, which is important. This is Azure Premium Storage. So this is the remote SSDs to the log service. So it's not local on the log service box necessarily. I mean, it's remote SSD to the compute at least. Sorry, it's remote SSD to the compute. And then the third part is the long-term storage, which is used to persist beyond what is on remote SSD. So that remote SSD part actually has 1 terabyte of space, and it's circular in nature. So it's flushed in time to long-term storage. And so the remote SSD part, it's just like a log on, with a few minor differences on disk on a VM or on Azure DB. So you still have VLFs, and you have log blocks, and you have log records, and that part doesn't really change at all, right? So the landing zone is what's the durable commit point. So when a commit is issued, the commit is not done until it's persisted, it's durable on the landing zone, okay? In parallel, asynchronously, we do copy it to the xlog process, so the xlog process doesn't have to read it from the landing zone. So compute itself asynchronously copies it to the process to be in memory. And that xlog and that xlog process actually then disseminates that data to page servers and replicas. It actually has this broker process, which is a hash map of every log block with a filter. So when a request, if a page server, if it gets a request, hey, give me a log block, it knows what page servers to send it, and so on and so forth. So it's a filter that allows it to smartly route some of these log blocks, right? And then the xlog process is also responsible for destaging the landing zone to long-term storage. And the destaging is done in VLFs. So it's, the full VLF will be destaged at a time, not a portion of the VLF. As VLFs fill up, it's destaged. And then long-term storage, of course, Azure Storage has built-in resiliency that we all know about. So what's this RBPX? Yeah, go ahead.
What does infinite mean?
Okay, nothing is infinite in life. Huh?
You're still clearing the log.
No, you don't clear the log. I mean, so landing zone is cleared, right? So infinite as in, okay, so in today's world, right, on-prem, you have to do a log backup, correct? Right. To clear the log. Yeah. Or you have to size it if your transactions go over, if you have an open transaction over 1 terabyte, you have to size it, right? I mean, here you don't.
In that sense.
You know what I mean? So here it just takes care of it. It'll destage as needed to long-term storage. Nothing in life is infinite. So let's just be, yeah, with respect to your workload. So how much we store in long-term storage depends on retention, retention period. So right now we allow you to restore to a point of time, right? So that much at least we have to have in order to seamlessly allow you to restore, right? So we'll get to that. So RBPX. RBPX is this caching layer on compute. It's a non-covering cache, and it effectively is a layer that intercepts this I/O. So if you see, look at, so all buffer pool interacts with the data via this data FCB, which is a file control block. So when a write page request comes, it writes to the xlog service, right? I mean, we talked about remote log service. In the same time, it can actually cache that data so it doesn't have to actually get it back to RBPX, right? And then similarly, on a read, when it's reading something from page server remotely, once it reaches this layer, it makes a decision whether to cache it or not. It doesn't cache it necessarily on the first read. It may be the second read that caches it. So there's some heuristics around kind of what gets cached and aged out. But RBPX is that layer that sits on compute. This is more of the compute part I'm talking about. It's non-covering, so it has some heuristics. And then what is cached and not is stored in this hackathon table or in-memory OLTP table, which has metadata. It's a page table that has what pages are cached and so on and so forth, if they're valid or not, some other details around that. So we talked about page servers full, cache, compute not full cache. the RBPX is 3x the memory on the tier. So if it's a, I don't know, 8V core has 50 gigs of RAM, RBPX is 150 gigs of SSD on that compute is reserved. That's the ratio. It's 3x the amount of memory for that tier. And then all RBPX I/O, here's the difference. All the I/Os from RBPX are actually 8 KB reads or writes because it's buffer pool, right? Buffer pool deals in 8 KB pages. A normal SQL Server read can be from 8 KB till 4 MB. Anywhere in the spectrum, depends on if you're doing read ahead or so on. But RBPX is 8 KB. So how does it happen? How does it all tie together? So you have a write I/O process. A user transaction commits. Commit actually lands it to the log, right? And then log actually asynchronously, I should have made this a dotted line, puts it in this broker, right? But once it lands it in log, the transaction is done. It's committed, right? We don't care about we'll asynchronously actually send it to the page server, and we'll see the read part of it, of how that happens, right? So the log service will then ship it to the secondary and to page servers. And then at some point, destage will kick in, and the filled up VLFs will be destaged to storage. Okay, the read I/O part is a little different. So from a cold start, so when I say from a cold start, this is not a restart of compute. This is everything crashed, page server crashed. Like both copies of page server crashed, right? So that's the only time we are actually going to read from long-term, blob storage into a page server, because you have to seed that, right? Or if one page server goes down, then we spin up another compute for that page server, and we seed it because it's a covering cache. It has to have all the data in all the files, correct? But this is not like if you do a slow upgrade of your tier upgrade of your compute or fail over your compute. Compute will just talk to the existing set of page servers that exist. So nothing goes wrong there. And then data files will be populated, right? And only the non-covering RBPX. So as we said, this is resilient, right? So if the compute had a page table entry with some pages that it thought was in RBPX, it will push those up and seed those in RBPX in compute, right? So if queries is made to the primary or replica, it doesn't matter. If the data is in cache, it's returned directly. If it's in buffer pool or in RBPX, it's returned directly. You don't have to go to any other layer, if you will. And then if it's a cache miss, then it requests a particular page from the page server at a particular LSN, because it has to say, give me this page as of this time, right? If the page server has that page as of that time, because remember, log records are being applied asynchronously, right? Then it'll return that page, no problem. If it doesn't have that page, then it'll actually ask the xlog service, hey, give me this log blocks till this LSN for this page. And it'll get the log blocks for the LSN till that page, and then return that page, and read is complete. Okay? Any questions before we, yes? Azure Blob Storage. So this is the, oh, yeah, this side. This is the layer where it's totally persisted. This is also has local SSDs, and it's a covering cache. What's that?
So when you say page server, you're talking about data file pages.
Yes. So each page server has one data file. So each 128 gig chunk.
Okay, so the page itself is 8K.
Yes.
But you store enough pages to fill 128 gig.
Yep. No, I'll rephrase it. So a database in Hyperscale has n number of files. Each file is 128 gigs. So each page server directly today, I can't say tomorrow it will, but today it correlates 1:1 to a file. Yep.
So the secondary has its own set of files, or it reads
Nope.
from the same files?
It talks to the, okay, the question was, does the secondary have its own set of files? No. The secondary is just a compute All it does is it has connections to the same set of page servers servicing. Otherwise, it would be super expensive and too expensive to run. Yeah. Yeah.
So there should be no latency reading from the secondary after the primary upload?
No, that's incorrect. Okay, the question was, is there a latency in reading from the secondary? Yes, there could be a couple milliseconds latency because it's not a synchronous commit. You persist, the transaction is actually committed when it's persisted to landing zone, right? Then log service ships those log blocks to replicas and page servers. So there could be a couple milliseconds latency.
But is it smart enough to wait till it's, my scenario is, basically I update the record, but I read back from a secondary. Is it smart enough to wait for it to be hardened or no?
So not in all cases. In certain cases it is. It's not synchronous, so there's no guarantee that every record will be there. We still do that get page at LSN. So if you have some pages which are not at an LSN and you want data as of latest page, you'll cache those pages up. But it's not necessarily guaranteed that the last LSN which is committed is there. No. We are working to expose some DMVs or some diagnostics to expose what's the replica lag. But today, today there could be a couple millisecond delay. Yes.
So this design is on purpose.
Yes.
On purpose, so we do not block your writes because you want highest throughput for your writes. You also want highest throughput for your reads. And we don't block one for other.
So I'll take that. So yeah, I get the use case, right? If you want a guarantee, there's one use case, but this also allows us to scale tomorrow to 15 replicas, 16 replicas, and not overburden your primary to ship all those log blocks synchronously to all, right? So it's a trade-off decision, but it is the decision. It's how it is today. Yep.
When you, as part of this, you can sort of resize your between these 2 and 8 cores.
Uh-huh.
Does that sort of involve cold start these servers?
Nope. No. Page servers exist. I will show you a demo. So we'll move to a demo, actually. So we'll see it working rather than talk about it. So I'm going to do a security principle that I shouldn't. I have a super complex password, so don't look at it. But I didn't have time to rewrite any tool or whatever. So anyway, so I have, actually, let's go to the portal first and look at this database. So if I hit configure, so I'm at a Hyperscale database first. Let me double check that, make sure. So this is around 4 terabytes, right, in size. I'm going to hit configure. And then the reason I'm doing this is so that we don't wait. So I have 1 replica already. OK, I'm just going to scale it to 2 replicas and hit apply. And I'm not going to time it or anything. It's under a minute, trust me. So now we'll go to actually a workload and actually look at a workload. So I have a workload. It's going to go only to the primary so that we can benchmark baseline, right? So this has 150 threads. Read scale out is false, and this is 150 threads. OK, so I'm going to start this workload. Oh, it's already running. Hold on. Let me make sure it's a fresh run. Didn't realize I left it running. OK, so this is initializing the workload. And you'll see this transaction count is increasing, or you'll see it increasing because I zoomed in, it stopped. And it should settle at around, so actually, let's look at diagnostics. I have a dashboard here. Let me switch. Yep. OK, so this is where we stopped. I'm just going to switch it to the 5 seconds. OK, but it'll settle down at around 1.5K. It was already running. I shouldn't have actually stopped it. So this is going to settle down in a second at around the 1.5K mark, right? So this is a baseline in terms of, if I only had primary, how long would that take? Also, you see this CPU is taken is around 60%, right? And so this part of the demo is just the read part of my workload. What if I had additional write part of the workload where I was now pegging CPU or resources on the primary? And again, I'm not demoing it with much. This is just 10V code. It's not very big, but at some point you can scale up only this much. And so how would you scale out in this case? Right? So we've plateaued there. CPU is our main bottleneck. We don't see anything but CPU. If you look at this weight, it's SOS scheduler yield pretty much, which is indicative of CPU. This is weight stats. There's no other I/O weight or anything of that sort. That's your primary bottleneck. Okay, so I have added, I have a replica already, and this should have been already added. It's still being added. No, okay, the replica is added. That's a different restore I was doing. The replica is already added. This should be two replicas now. So that was it's less than a minute, maybe a minute or so. And I'm going to scale out these workloads now. I'm going to stop this workload. Go to the profile, and all I'm doing is changing true to false. Oh, false to true. Right? So read scale is true. Actually, one thing I didn't do, actually true is fine. And I'm going to run. And I should have shown you actually the queries were landing on the primary replica, but I will show you in a bit. So that is scaling up. And you will see that, in a second here, this CPU is dropped. This batch request has dropped because this was monitoring just the primary. Right? So the workload on the primary has quiesced pretty much. But we are getting around, or we should get around 1,400 transactions a second, right? So we've scaled that workload to the read replicas, or offloaded that workload to the read replicas. Because it's read intent equal to, or application intent equal to read only was specified, and that same workload was scaled to the read replicas. So how can I see if this was actually scaled off to the read replicas? So I'm going to make a new connection. I have to actually copy this because I don't want to type it. That's fine. Options, additional correction parameters, and I'm going to say application intent equal to read only. That's the only change, right? And you have to connect to the database, by the way, okay? You can't do that and connect to the logical server. If you have app intent, you have to specify database name, otherwise it's going to fail. Or you won't get the read-only connection you think you would. Right, so I'm going to take this executing request, which I should have showed you on the primary, but we will get a chance to see that, and execute it once. Right, and you see now, I will show you on the primary in a second, but this host name would have been different than the primary. This is DB51. Just keep this in mind. You see that requests are actually on the secondary now. We'll keep this DB51 in mind and actually show you another connection, right? And you see that CPU on the secondary, which is DMDB resource stats, is the DMV we use to see. This is what Portal shows you in terms of CPU, data I/O, and so on and so forth. On this secondary replica is consuming now, 30-odd%, right? So let's make another connection with this, hopefully. Hopefully we'll land on unfortunately today you cannot specify I want to connect to replica too explicitly. It's a round robin thing. So I hope I fall on another replica, and I was lucky. Good sign for the session. And I fell on a different replica. This is DB54. Right, this is the host name in one of the XC collectors. So DB54. So this is a different replica, and I see queries on that second replica as well. Correct? And then I see that the second replica also is consuming CPU. Okay? Well, you would say that's not fair. Use the same 150 threads, and now you have 2 replicas. Of course, it's going to scale. So let's go change that profile. Right? We'll make that 300 threads because we double the replicas. Oops, not 300,000. That wouldn't be good. And then we'll do one better. But wait, if you call now, there's more. We'll add 150 replicas or threads on the primary. OK? And I'm going to launch this. I hope that was not running. Yep, no, it's not. And this will take a little longer to initialize, of course, because now it has to send the workload to all the 3 replicas. And we'll see what this lands at in a second. So now, actually, if I go, I have queries on 1 replica, which is DB54, or you will have in a second. And you should see on the primary as well, which is DB52. So you have DB52, 51, and 54 is, I believe, the 3. That's 1. This should be the second. Yeah, 51. And this should be the third. Right? So you have 3 queries, and let's go back and see where we landed. It's still going. So I mean, we landed around close to 4,000, batch requests per session. So you scaled out this workload, right? So it's pretty evenly going to scale. So we had 1,400, not totally linearly, but close, close enough. So that's how you would scale out your workload. Adding a replica less than a minute. You can scale your read intent across replicas, so on and so forth. Let me do a time check. I'm usually not great at time management. OK, so move on to the slides. OK, backup restore. I'm not necessarily going to go into a demo of this. There are several videos of 50 terabytes in less than 20 minutes restore. But I'll talk about how this is done. So you have page servers like we talked about, right? Each page server has its data files. So at regular intervals, and I don't want to state a time because that time could change. It's our internal stuff. We just guarantee that you'll be able to restore, right? So at regular intervals, we take snapshots of these page servers. And all of them don't have to line up to one interval. It could be a snapshot at millisecond 1 and next minute, whatever. Right? They don't have to line up to the exact second across all page servers. And then you have the landing zone that we talked about also, which has stuff in it. And then you have long-term storage for the log, which also has some amount of stuff in it. Right? So backups don't have any impact. So say you want to restore to a point of time where that line is drawn. It's a point of time X. Right? So what happens? We take the latest snapshot from each of the page servers to that point in time X. Right? And then we mark the long-term storage or landing zone to kind of the transaction, the LSN at that time X, that you want to restore to. And that becomes your point-in-time restore. And because of ADR, we don't have to go back in the log to your oldest active transaction because each checkpoint actually does flush some pages, and ADR does something smart for recovery, right? So we take the oldest as of what ADR needs to recover you, and then copy that to another set of Azure storage and long-term storage, right? So the snapshots are just, it's not size of data, just the snapshot markers are there, which actually snapshot that stuff into storage which will be dedicated for this new restored database, right? So you're restoring a database as a copy of something. Then, yep.
So with Hyperscale, that means we don't need to create backups. Like in Azure SQL Db, we are so advised to have backups, right? So do we need backups?
So the question is, do you have to create backups in Hyperscale? Even in Azure SQL Db, the system does take backups, and you do have a point-in-time recoverability. So I mean, if you can.
Yeah, because they were saying we should back up into like our own
Yep. So, yeah. So the yeah.
You worry about only restore. We worry about backup.
So. Yeah, so the only reason you would want to quote-unquote backup, I don't know if you mean backup of the database or backup in terms of backpack so you can actually pull out data somewhere else. Those are two different things, right? No, yeah, backing up the system should take care. I mean, there's no point of a PaaS service is not going to back it up for you. So all our PaaS offerings, do backup stuff. So then we spin up, it's constant time restore because irrespective of the size, it's just snapshot there, right? Then we instantiate compute for the page servers for the new database in question, right? And then, oops, my clicker is. And then we instantiate primary compute, and then we do recovery on that tail part of the log so that it can, so some of the time is not only snapshots. Snapshots are copied in parallel, and then recovery is done on the tail to bring it to the endpoint. So you can get 50 terabytes or 20 terabytes, it doesn't matter. It's generally the time frame is between 9 and 20 minutes. It depends a bit on recovery and what else is in the log, but it's generally is that time frame. Yes? Yes, sir.
Let's say a region failure?
One more time?
What's the ROA, or let's say region fails?
If the region fails, today point-in-time recovery is only within region. We will have, upcoming in the roadmap, we will have GODR to other regions. So there's, today Azure SQL, so the question was what happens on a region failure? We have, in all our SQL offerings, we do have GODR, which you can have a replica in another region, to protect from region type availability. And that would be coming to Hyperscale. So it's not there right now. I have a roadmap slide if you hold, yep. So the storage is, storage still, RAGRS. So storage is geo-replicated. So, I don't, I can take it offline. I think we can, but I want to say something incorrectly. So just sync up with me later. I will give you the for sure answer. Yeah, go ahead. So today it's not there, but it will be in private preview very soon. So.
The other thing about backup and restore is crossing.
Region boundaries. Huh?
Crossing pricing. So if I wanted to go from Hyperscale.
Yeah, so let's hold that. I have migration. So there's some roadmap items and some stuff. We'll hold that question for a second. And ADR is used, so that's that. So I'm not going to, in the interest of time, if we want, we can come back to this. We have a couple other demos. I think we'll skip the VLDB because I'm not going to wait for 20 minutes, so I would show you a completed one. So why Hyperscale, and then we look at some diagnostics, right? So even for your smaller databases today, due to the multiple caching layers, it can perform better than general purpose today, right? So it's if price point is between general purpose and business critical, it performs better than general purpose, even for your smaller databases. So irrespective of size, I wanted to say, I mean, performance is better than general purpose, and in some cases, I mean, depending on a workload, you could maybe not need a business critical and go with Hyperscale, but that depends. Right? Offloading backups to page servers does free up some resources on compute. We have the rapid scale up and scale down problem. So in business critical, one of the problems today is if you want to go from say 16 cores to 24 cores, if there's no space on the node, it has to bring up compute and seed because it uses always on availability groups, right? So, I mean, a database is available while seeding is going on, but that seeding process is 1 gig a second, you know what I mean? And so if you have 2 terabyte database, that could be a while until the actual switchover. The switchover is only 10 seconds or 15 seconds, but the seeding can take a while. So this, scale up, scale down should take, generally 60 to 120 seconds, somewhere there. Read scale out with primary plus 4 replicas, we already saw that. Snapshot based restores. The caveat here is if you require super low latency latency in the 1 millisecond less range for a commit, business critical might still be the tier you want to go to. So if you have a very low latency requirement for a log commit, BC might still be the best. And this is more for small transactions, you know what I mean? Yep. Then the size, large databases up to 100 terabytes is another pivot. You have, you don't have to worry about kind of log space, and this it just scales from that perspective. Storage is decoupled from compute, so you can have a small compute on large storage, from that perspective. And then workload patterns. Of course, you have the OLTP. You have more of the hybrid, which is OLTP with some level of real-time operation and analytics. One second. And then you have operational data marts, which are there, often to front-end dashboards and things of that nature. And you have IoT and some other near real-time scenarios which are enabled with this. You had a question?
Do you have to size your storage from the beginning, or is it
Nope. You start at 0 and you end where you end. Okay, the question was, do you have to size your storage? And the answer is no. We grow in 10 gig chunks, and we, yeah.
You shrink back?
No, we don't shrink back, no. So some of the scenarios, yeah.
How often the snapshots made?
So that doesn't really matter from a user perspective, right? You have restorability time, in terms of we'll restore the last. Today it's 7 minutes, but I don't want to quote that number because that can change. It doesn't really matter. We take the last snapshot and then we apply the log, right?
But we make a snapshot more often, the restoring time will be shorter, right?
Yeah, it could be shorter, but the ADR is there for that, right? So ADR also, does play a role in restorability. Yes, but it's also a balance of COGS and cost, right? So we would have to increase, if we did a snapshot every minute, we would have to pass some of that cost because it costs more, right? So it's a balance of we'll try to keep that restore time within a manageable time, right? And if you have to change the underlying plumbing, it should just work for you. That's the goal, right? Yep.
You say you don't shrink back, but if your growth, your database progression, you drop a bunch of data in there and merge it off.
Uh-huh.
Does the storage always stay there?
The unallocated pace at this moment, yes, it does. And we've got some feedback around that. We're looking at some of the models. You build for use space, but yes, right now we don't shrink because shrink operation is a little more complex today because you have to deallocate a page server and some other stuff. So we're looking at, what can be. Today it is, yeah. For a normally running database, you shouldn't have a problem. It's more for the test scenarios where you grow. Because to be honest, in the storage, in the whole architecture, right, the storage cost is drop in the bucket compared to everything else. Because it's a blob storage, so storage price is not the expensive part of the equation. It's pennies on the dollar from that. Not to trivialize any cost, but it is the cheapest part of the system. So near real-time fraud detection. Oops, I'm running behind. So we have the scenarios, we have customers doing things like this. It's a classic, it can be fraud detection, or it could be IoT, or it could be some combination thereof, where you have some data somewhere, whether it's on-prem or originating on devices. If it's on-prem, it goes via some ADF or pipeline or Airflow or any of your orchestration tools. And it's brought to Event Hub with Kafka API or without Kafka API, it doesn't really matter. And then you use a streaming type of scenario where you're using Azure functions. This was an example of an actual customer. You use streaming functions to pull that data off of Event Hub and land it into Hyperscale. And Hyperscale, in this case, they wanted to scale out more. Some of the scenarios, you ingest on one node and you're reading on other nodes. And they didn't have the synchronous requirement. It was OK to have a couple milliseconds latency. And so they didn't even scale up as much as they could. Actually, they kept each node modest size and scaled out to 4 replicas. Right, so that's, one type of scenario. And then they have the other pipeline where it lands some of this data into Azure DW for the large scale stuff, because this, here in the top part, they've actually segregated based on some customers and usage scenarios, so they can expose different things to different people, sets of people or their customers, right? In here, they're pulling some other data as well as this data, and just have like hundreds of terabytes in DW. Sitting, yeah. So I mean, it's the use case of what type of queries, right? So the question is, why go to the DW at all, right? First of all, that DW has more reference data than just the streaming data, right? Second thing is, I mean, it's an MPP system, so there are certain classes of queries. Like I said, a query. So for example, in Hyperscale, they're maintaining it 16 cores or 8 cores. That's not going to scale for some of the patterns of queries like DW can, in the sense that if you're doing over a large set of data, which is a composite of all these different customer bases or use cases in one place, and you want massive, this DW is the place to go because it's a parallel execution engine. So, and then they're doing some automated analysis and such. The other places we are seeing, I mean, here also this customer has DW, but again, I've seen customers without DW if it's just data marts and you don't need to consolidate everything, right? So here they're doing more of A/B swap testing. They do truncate and load, right? And it happens every so often because they get customer data. And so they load into one, and then at the end just rename. And then queries go to that. So once they load, it's not a trickle load, it's a batch load. It happens end of week. It's predictable, so on and so forth. So they load into a new database and they swap. So just rename, yep.
Can you envision a future where maybe this becomes
Yes.
the de facto engine and takes over for DW?
Oh, no. I said yes before I heard the question. So the question is, that was tricky. My fault. Can you envision a future? Can you envision a future where Hyperscale becomes the de facto engine? Anything is possible. I don't. There's no near-term plans. There are different use cases.
You are giving me business ideas, so
we can chat offline. Yeah.
It seems like the natural evolution of DW. Not
Okay.
Snaps, but DW, the DW resource.
Yep. Let's. If you want to see more demos, we need to speed up a little bit. Resource management. I'm going to go to some demos. Is that okay? Rather than talking about slides. So we'll look at some scenario around. So I want to actually cover this one. Performance tuning is no different, right? It's the same thing. The only thing I'm going to show you is a set of weights which are different. So you still start with what resource is consuming most. Then is it CPU bound or it's weights? And if it's weights, you troubleshoot the weight. What we'll look at are now is hyperscale specific weights, which you might have not encountered before. So for that, I'm going to look at, the first one has to do with tuning data load. And so I have a Spark notebook here. And all I was doing is I'm reading this file from my storage account, right, or set of files from the storage account. I just defined what the schema is for that file type. Nothing spectacular. I want you to focus on the SQL part, not the Spark part. And then I'm loading it into this table. Right, batch size 100,000. Tab lock is true, and there's a timeout which is kind of irrelevant for this discussion. So I start the load, and we'll see that this load is going on. So we have 16 tasks only. Yeah, okay, 16 tasks running. Each of them is actually bulk inserting. So let's go to actually the SQL side and look at it. So if I look at executing requests, oops, wrong server. Actually, I don't need even to look at this. So I'm going to go to the dashboard and actually look at this database. It is for SQL Db. Right? So we see that, well, log write percent is at 100%. First thing, this is the resource stats DMV. So this blue line has reached 100%. So we are not going anywhere, pushing more data, right? So one of the questions is why DW? I mean, your log is capped to 100 Mbps on Hyperscale. If your ingest requirements are such that you need more than that, today at least, I'm not saying tomorrow, you can't you can't do it. Yeah, I'm giving him hope. Yeah. So we'll see a couple of things. We see the log generation rate is at around 95 megs a second. There are 16 streams going, and we're going to see a couple new wait types. I think, hopefully. Oops. Where's it gone? Yeah. One is this wait RBIO replica. Right? The second one is wait RBIO destage. So what are these? So remember we talked about the destaging process, to destage from the landing zone to blob storage from the log service. This is a wait type that's saying, hey, that place is getting full, so I'm destaging it. So this is a wait type to do with that. The second thing is wait RGIO replica is throttling log generation rate because we have set governance. The limit of log generation rate is 100 Mbps. So when you hit 100 Mbps around there, I mean, you're going to get the wait RBIO replica. You'll also get this if a replica is so behind. So if a replica is behind or a page server is super behind due to whatever reason, we will throttle log generation rate on primary to some extent. And that's true even on GODR today, on non-hyperscale, even on BC GODR. If a replica is behind, because we don't want to get that much in sync that we can't hit an SLA on something. So we will throttle replica. And so I purposely here overloaded 8-core log generation rate where I had 16 threads going. So these are new wait types actually that you will see that once you hit that limit, you need to back off from the amount of concurrent bulk inserts you're doing, right? And I can show you how to back off, but that's just less threads with bulk insert. You can repartition in Spark or coalesce in Spark, or if you're using some other framework, however you code it, it doesn't really matter. So in Spark, I'm not going to actually, no, actually I should do this. So in Spark, what you would do is, I'm just repartitioning to 4 streams instead of 16 streams, and let's see if I get rid of that wait type and still maintain throughput, right? So I'm just sending less streams, but I should maintain the same throughput, because if you overload the system and you're waiting, it's not, your cumulative throughput is still 100 Mbps, so there's no point in actually taxing the system beyond what it can. And log generation rate on Hyperscale is not tied to tier, right? In GP or BC, it could be tied to tier. So if you have like 8 core versus 16 core, it's not a different log generation rate. It's the same 100 Mbps across the vCore spectrum, if you will, right? But having said that, if you have less than 6 or 8 cores, you're not going to hit 100 Mbps. You're probably going to hit CPU bottleneck before that. If you have 2 cores and you have 4 streams going, you're going to hit a CPU bottleneck before that. So at least 4 vCores and up, probably you can hit that. Okay, so I'm repartitioning this, and this will take a little bit longer. Not from the. I want to show you that it's not from the SQL side, because the first part is actually coalescing those into 4 streams. So it's, this first stage is the Spark stage. The second stage is the SQL stage. So, I mean, once this is done, we'll come back to it in a second. Yeah, so data I/O we'll talk about next. Just good. It's almost like I paid you. Maybe. Actually, I'll cover it in this itself. So data I/O cap is currently only for local RBPX I/O. So what you see, I mean, these all I'm pulling out of this DMV called user DMDB resource governance. And here, the max for this 8 vCore is 20,000 IOPS, right? But this only governs RBPX IO, which is the 8K IOs. There's no governance currently into what is fetched from remote page server. Of course, at some point of time, you're going to exhaust stuff, but I don't think we've seen that yet, at least. Because so far, it's 128 gig chunks, so you're not like landing on one page server when you query data, or the likelihood is less. And so the governance right now, though, is it has to be a bit better documented, which I'll take on in terms of what's there. Yeah, sounds good. Thank you. So where was I? Okay, so Spark stuff. Okay, so that part is done, and now we are actually loading records. Right, and as you can see, I mean, each of these stages, there are 4 threads loading, and we have loaded, I don't know what, 5.7. I can't read 5.7 million each so far. And it'll get done in a minute, right? So each thread is loading about 11, 12 million rows, and in about a minute it would get done. So let's switch back. So these are your weights, and I'm not. I mean, the link has all of them, so the links are in the slide. I'll upload the slide deck as well, so it has more description on what those weights are and why. So these are 4 most common ones you'll see if you're stressing data loading, if you will. Right. So on the data side, so that was log side. Right? On the data side, you'll see page IO latch still, and that's a bit of a I mean, so you see page IO latch whether the read is from remote or if it's from RBPX. So you can't distinguish right now between the two. Just IO latch is the fact that you're waiting on IO, right? So that's that. And write log includes time to harden to landing zone. It's not necessarily that anything is throttled, but if it's the time to actually harden the log to the log landing zone. So we've covered all the weights to do with read and write in a way. So this is a reference slide, not going into it. This is a normal data loading tips, which is this. So IO counting, let's go to IO counting. So how in the world do I know if my read is coming from RBPX or if it's coming from somewhere else? Right, so we have added these page server reads columns to all your existing set of DMVs. So DM exec requests, procedure stats, query stats, and they will give you for a query how much is a remote read versus not. So you can determine then so what's the solution to that, right? Actually, scaling up compute is a solution to that because you get more cache. If that's a latency, I'm not saying it's the only thing. That's one aspect of it. Scaling out is another aspect of it also because now each of the replicas has their own local RBPX cache, as well. So we're working on improvements always to make the latency of page server less, but it is where we are. Page server reads are also added to the actual execution plan. How many of you have seen the recent improvements to actual execution plan? It has weights, it has reads, it has per thread execution stats, so on and so forth. So page server reads also has been added. So if you have an actual execution plan, don't look at estimated, you're not going to get that. It's only in the actual. Right? And page server reads, just as of last week, thank goodness, has been added to query store as well. So you can look at the query store queries that you know and love, and don't forget to add page server reads to those columns being returned. Along with logical reads, also add page server reads. RBPX IO. Okay, 1208, wow. So RBPX IO is exposed in a DMV. It's this virtual file stats, and it's file ID 0. And there's a bunch of details in that Hyperscale diagnostics. So how about this? I'm going to finish a couple more slides, and then we have time. I will do the last demo. Because this is super important. Right? So index creation and rebuild. One of the problems with VLDB is you have VL tables, right? Very large tables. So TempDB is limited on Hyperscale, just like any other SQL instance, because TempDB is local to compute, right? So there is only so much hard disk space in compute, and so if you're reindexing a table which has a gazillion rows, you're going to get an error after a while saying that TempDB out of quota, right? So our guidance is to use resumable index because resumable index breaks that index operation into multiple chunks, right? And can free up the log, during that time frame. Even the merge sort operations actually on tempdb are chunked into transactions of less size, if you will. So if you also so it's supported in create index also as of very recently, last few months on Azure. There's also, if you have scripts that exist today that you don't want to change to use this option, there are database scope options for to say that, hey, elevate resumable equal to on or when supported. So your script can be without resumable index, but under the covers we'll change it to resumable index when supported. If you don't want to change your script to actually have the plumbing for resumable index. So that's another thing. Maxdop hint for create rebuild is another one. I would strongly suggest that, in particular, if you're doing a data load scenario, right, where you're building multiple concurrent indexes at the same time, and that's to reduce the memory grant size for each, so that they don't hit resource semaphore contention. So maxdop hint also is one we should this. Now, from a pure speed perspective, offline is still faster, right? Online has additional overhead. We have commit of the chunks. So I want to put that caveat as in, if you need, if you can use offline, and your scenario that you have a pipeline that loads data in index and you want it available as soon as possible, then use offline if it's faster and it fits. So new DDL syntax, migration. Migration today, you have the Azure migration. I mean, the migration story, effectively, the recommendation is to actually do some sort of logical data movement. Our story is evolving on that, and we hope to have a much better story. DMS exists today to migrate to a hyperscale database. You can use any of the methods to bulk load copy data, and I'll tell you in the next slide why this is. But ADF or Spark or Smart Bulk Copy is a sample that exists to load and then rebuild your indexes. You can use transactional replication, but if you're doing that, then use concurrent snapshots. Otherwise, snapshot can become a bottleneck on the source, if you will. So we don't have a restore into Azure DB today. So that's been a feedback item we've got, right? You have a larger database. How do you restore it? And so that's something that doesn't exist today. So I mean, today you're limited with some of the options. Backpack exists and works for smaller databases, but if you're talking terabytes, Backpack is not going to be the option unless you start partitioning tables into separate backpacks, and it becomes a little more painful, if you will. Migration from existing SQL Db. So here's also there's a caveat. So migration from existing SQL DB, you can just do a tier upgrade, right? Today, and it's a one-way street. So it's not quite Hotel California because, but I mean it's a one-way street, as in there's no reverse going back to the previous tier at this moment. We've got that feedback too. We're looking at what can be done, but even for existing database, when you go, if it's a performance-sensitive thing. Currently, if your data file size is greater than 128 gigs, so we had two architectures of page servers. When we GA'd, we actually started with 1 terabyte page servers, right? And then realized soon after that that's a performance bottleneck because remember the lowest level is stored in Azure Blobs. And Azure Blobs has a per blob IOPS limit and some other throttling that happens if you have large blobs. So we broke that 1 terabyte down to now 128 gigs. And that will potentially see some evolution in kind of some of that page server chunk size. But if your files are greater than 128 gig, there's no way for us to break that up, right? We're not going to shrink DB and reorganize on the fly. That's not going to work. And so I mean, you land up on 1 terabyte page servers, right? 90% of people, 95% of people are fine, right? Because given it was a slow migration or tier move, you didn't have a huge database, so it didn't matter. And it's only for your existing files. All new files will still be 128 gigs, right? But there are some people who did run into some customers that did run into some performance problems, right? And so option one is the easier one, to be honest, if you can afford the copy aspect. So copy into a new hyperscale database. In particular, if you're you have like a 1 terabyte file and you're just using 100 gigs in it. So when you have a 1 terabyte page server, you're still going to use that page server a lot for all new data until it fills up before we spawn up new page servers, right? So that's one option. The other option is, of course, we can add files and rebuild. So add files is a DevOps operation, though. So it's not like you can do it. But if you run into perf problems, then open a support case, and then we can see what we can do about it on the back end, right? So coming soon, change tracking. Coming soon as in it'll be in private preview very, very soon. These are some of the gaps we had. Change tracking, database copy, in terms of database copy to another region, another subscription type stuff, right? And then GeoDR, which is geo-replication. And then the feedback we've heard is long-term retention up to 10 years of backup. We don't have it yet on Hyperscale. And then the TDE BYOK, is in plan. So I am at the top of the hour. Sorry I missed a demo. There were good questions. But experience Hyperscale, documentations, and then please fill the session evaluation. Would love to hear feedback on how I can improve as a presenter. Thanks. Yep.